Welcome back. In this last part of lecture 8.2, we're going to talk a little bit about the normal distribution. Now, this normal distribution is really probably the absolutely most important that we've covered in these standard distributions that over the past couple lectures, except for possibly the Poisson could be considered of a similar level of significance. But yeah, in some sense, this normal distribution is like some sort of universal object. It shows up all over the place. We'll see this later in the course when we get to the central limit theorem. For the moment, I'm just going to introduce the definition and also see some sort of abstract reason that hints towards why it's important. Okay, so the normal distribution, we denote it with this curly n. That's terrible curly n, I'll redraw that. Yeah, that's close. With mean m and variance nu, which are words that you don't need to know what they mean yet. Where m is in R and nu is greater than 0. So is the probability measure on R with its Borel sigma algebra with density phi m nu x is equal to this 1 on square root 2 pi nu e to the minus x minus m squared on 2 nu for x in R. Okay. And just to give you an idea of what this looks like, I've got R here, you've got your point M, you've got something that sort of decays like this, except much quicker than what I've drawn. Yeah, let's just redraw it. So it's sort of like this, and then very, very quickly, almost 0. But yeah, I've drawn it a bit badly. This is an exponential of a real number, so it's always going to be positive, but it decays incredibly quickly as you get far away from m. And sort of nu here determines roughly how wide this is. The larger the value of nu, the wider this is, and therefore the shorter, the flatter it is too. Okay. And so I've said that this is a very significant distribution. Here's a kind of concocted example of why it's of one place that it arises, although it doesn't, it's going to seem very left field at the moment. So we have the following theorem. Okay, so let A less than B for n in Z plus. No, actually, yeah, no. Yeah, I'm getting confused with Georgie's notation. So in here, which is excluding 0, we let omega n be the ball of radius square root n in Rn. Okay, and u omega n be the uniform distribution. Okay. we let x1n from omega n to r take, well, it just tells you what the first coordinate is. Okay, so this you can check is, well, very clearly a random variable with respect to the respective sigma algebras. And then the statement of the theorem is then the limit as n goes to infinity of u omega n of a less than or equal to x1n less than or equal to b is the normal distribution with parameters 0 and 1 of AB. Okay, well, you could ask, what is this even saying? So the idea is that, well, in one dimension, so n equals 1, you've got 0, you've got a ball of radius 1, and you just x1n is returning you your position along this line. If n equals 2, then you've got a slightly larger ball, pretend that's round, where this is root 2, and then you're just projecting onto this direction again. In higher dimensions, you keep doing this, and the idea is that then whatever value sort of, well, yeah, eventually, because the radius is increasing without an upper bound, these are eventually going to provide any real number for you, like take n higher than something and you'll be able to get further and further out. And sort of the reason that we take this square root of n as the radius is going to become clear when we look at variance. So for variance, then this scaling here maintains the variance for at each step. And what this is really saying is that if you take these these probability spaces and you look at the limiting distribution that you get on, in some sense, an infinite dimensional space, then exactly what you're getting is Gaussian in each of the coordinates. You can sort of rearrange this and you'll find that it works for any fixed coordinate. Okay, so it's saying essentially the uniform distribution in infinite dimensions should really be Gaussian in some sense. Like the Gaussian is definitely not translation invariant, but yeah, so it does turn out that if you're looking at an infinite dimensional space, you can't get a uniform distribution like Lebesgue measure, but you can very often get Gaussian measures like this. Okay, so this is one sort of abstract example of how the normal distribution just shows up, but there are a lot more very succinct and easy to understand ones that we'll see later in the course. One thing I should mention is that this N01, let's try again. N01 is called the standard normal distribution. And if you've got a random variable that is normally distributed, meaning its distribution is any of these n with m and nu, you can scale and shift your random variable to get it to a standard normal distribution. All right, so we'll see this guy a lot more later on, but this is just a little introduction so you can be a bit familiar with it. All right, so next lecture we're leaving behind all of these standard distributions, and we're going to move on to expectation and independence. Or no, sorry, conditional probability and independence.